Some other empirical probabilities which are interesting to look at. We have really good data in the US on cancer. And so we can say things like, what's the probability that a US male will develop cancer in his lifetime? It turns out to be 44.8%. So that's pretty high, right? The probability that a man dies from cancer is 23.1%. We can also look at the statistics for individual cancers. The probability that a man develops prostate cancer in his lifetime is 16.2%, so about a third of all those cancers that men are developing are prostate cancers. And by the way, the overall probability of cancer does not include non-melanoma skin cancer. This is excluding non-melanoma skin cancer. Notice, though, that the probability of developing prostate cancer is 16%, but the probability of dying from prostate cancer is much, much lower. That tells you a lot of those prostate cancers are not killing the men. Compare that to lung cancer. So the probability for a man of developing lung cancer in the US in his lifetime is 7.8%. The probability from dying from lung cancer, however, is 6.7%. Those are very close, so most people who get lung cancer are dying from it. We can see the same statistics for women. Interestingly, women have slightly lower chances of getting cancer or dying from cancer, 38% and 19%. That's largely because of smoking and drinking. More men smoke and drink, and those are linked to cancer. Breast cancer is the most common cancer for women. Her lifetime risk of getting breast cancer is 12%, but her lifetime risk of dying from breast cancer is much lower, only 2.8%, sort of similar to the prostate cancer for men. In contrast, a woman's lifetime risk of developing lung cancer is 6.4%, slightly lower than for the men, but that gap is narrowing as more women are smoking relative to men. And her probability of dying from lung cancer is 5%. So again, lung cancer is a very deadly cancer compared with breast cancer. So now let's do some actual calculations of some theoretical probabilities. I'm going to show you a few examples of how to use what are called the counting methods for calculating probability. These apply when you have situations where all the outcomes are equally likely, and we're literally going to be counting up all possible outcomes, and we're going to be counting the ones that fulfill the event that we're interested in, and so literally that's why it's called the counting method. Things that have equally likely outcomes are things like cards. It's when you draw a card out of a deck of cards, all the cards have an equal likelihood of being picked, or if you're rolling a dice, all the sides of the dice have an equal likelihood of coming up. So these counting methods are for this type of situation. So let's just practice these. Again, I think these are fun to calculate. So they're great for gambling too. So a lot of, if you really want to know how to calculate poker probabilities, you need to know the counting methods. If outcomes are equally likely to occur, we say is that the probability of A occurring, you're going to put in the denominator, you're going to count out the total number of possible outcomes, and then you're going to put in the numerator, out of all those total number of outcomes, which of those outcomes includes A occurring. So we're literally going to count those out, both in the numerator and the denominator. And these counting methods are pretty challenging. They're also sometimes called permutations and combinations. Some of you may have done these before. Most people find them to be pretty challenging. I'm just going to, in this module, give you a few basic examples. If you want to delve into more details, there's an optional module which will go further into the counting methods. So here's the first example. We're going to calculate the following probabilities. And note that all of these are what we call with replacement examples. So when you roll a die, if you roll a die once and you get a 6, and then you roll the die again, you still can get a 6 again. If you roll the die again, you can get a 6 again. So all your outcomes are allowed to repeat. This is in contrast to something like if you've got a deck of cards, if you draw the red, the ace of diamonds out of the deck, if somebody's already drawn that card, it doesn't repeat. There isn't another ace of diamonds in the deck. So that would be without replacement. But things like dice and coins have replacement. You can keep rolling heads, you can keep rolling sixes. So what's the probability of getting 1 6 when you roll a die? So that one's not too hard. So again, we're going to use the counting methods here. So think about what's my numerator and what's my denominator. So how many possible outcomes are there when you roll a die? So there's 6 possible outcomes, 1, 2, 3, 4, 5, or 6. That's our denominator. How many outcomes are there that involve getting a 6? Well, there's only one way you can get a 6, right? So there's 1 6 out of 6. So the probability here is 1 out of 6. So that one's pretty straightforward. The second question is, what's the probability of getting 2 6s when you roll 2 dice, or you roll, the same die twice? What's the probability that you're going to get 2 6s? So this one is only slightly more challenging. I want to start with again, the counting method way of solving this. There's actually more than one way to solve this. I'll show you both. That's one of the hard things about probability is there are many ways you can get the right answer, so it's often tricky to know which one is the most efficient. So we'll start with the counting method though. So what's the probability of getting 2 6s when rolling 2 dice? So our denominator here is going to be all possible outcomes that can occur when I roll 2 dice. So what can happen when I roll 2 dice? Well, let's draw out a little tree to help us with it. So when I roll a die once, there are 6 possible outcomes, each with equal likelihood of occurring. Those outcomes are you're going to get a 1, a 2, a 3, a 4, a 5, or a 6. So that any of those can occur on the first roll. Whatever happens on the first roll, I'm allowed on the second roll to have all of these repeat. I can get a 1, a 2, a 3, 4, 5, or 6. So let's say I get a 1 on the first roll. Then I could get a 1, 2, 3, 4, 5, or 6 on the second roll. 1, 2, 3, 4, 5, or 6. If I roll a 5 on the first roll of the die, I can again get a 1, 2, 3, 4, 5, or 6 on the second roll. You can draw out these little trees just to kind of help you enumerate all the possibilities. I'm not going to draw out the full tree here, but you start to get the idea. There are 6 possibilities on the first roll. There are 6 possibilities on the second roll because everything repeats. So if you were to draw out all these branches, you were to make all the possible branches here, you would count up that there were 36 branches. Well, how did I get that? There's 6 possibilities on the first roll times another 6 possibilities on the second roll. So my denominator will be 36 here. There are 36 possible outcomes when I roll 2 dice. And I'll just point out here that notice, like I'm counting, here's 1, 1, here's 1, 2. Somewhere down another branch will have the outcome 2, 1. So I'm counting getting a 1 first and then a 2 second as different than getting a 2 first and then a 1 second. That means that we're what we call in probability considering order. And all you have to know is that if you consider order in the denominator, you're going to consider it in the numerator. So you have to be consistent. So there's 36 possible outcomes here. How many of those outcomes involve getting 2 6s? Well, there's only one way that you can get 2 6s. You have to get a 6, and then you have to get a 6 again. There's only one branch if you did out this entire tree. So that probability is going to be 1 out of 36. Finally, what's the probability of getting a sum of 6 when rolling 2 dice? So what do I mean by a sum of 6? So that is you roll 2 dice, and what's the probability that if you add up the values from both of those rolls, that value will equal 6? So notice that our denominator is going to be the same here. There are 36 possible things that can happen when you roll 2 dice. So the denominator is the same. But to get the numerator here, there's no way to get the numerator other than just to count out all the ways that you can get 6. You can get a 6 by rolling a 1 and then a 5. You can get a 6 by rolling a 5 and then a 1. You can get a 6 by rolling a 3 and a 3. You can get a 6 by rolling a 2 and a 4, or by rolling a 4 and 2. So again, the numbers on both of the dice have to add up to 6. Those are all the possible ways you can get a sum of 6. I've enumerated them. I've written them out. There's 5 of them. So the probability of getting a sum of 6 is 5 out of 36. And notice, to solve the numerator in this particular problem, there wasn't any formula I could rely on. There's no formula I can give you. You just literally have to think it out. And again, that's what's really challenging about probability problems, is that I can't give you a pat formula that works for everything. In all of the problems, you really have to think about the problem and what's going on. And that's the great part about it, because it really makes your brain work, but students find that challenging because they want me to just give them some kind of formula they can plug into. Well, that's not going to be the case here. You're actually going to have to really think. So that's the first type of example. This is with replacement. The dice can repeat.